Okay, today's class let us focus on the very important synchronous binary counters. Last class I had given you a hint on this synchronous binary counter design. Today we complete this module, this topic. We want to discuss about mod 6 counter design also. Okay, don't make noise. If you have any questions, you can ask. You already see the difference between ripple counter or asynchronous counter and the synchronous counter. What is the main difference between these two? Synchronous counter one side, asynchronous counter. Clock, very important is clock. Output of one flip flop will be the clock of the next flip flop. That is the ripple counter or asynchronous counter. Synchronous counter, clock is clock. Common clock we apply for all the flip flops. Understand it? See, if you involve in this digital design, you may use this counter many times. Let me tell you that. Maybe in my career, I've used 1,000 times. I've used counter. I already showed you how to design a counter in the previous class, right? I use both combinational and sequential ideas to design a counter. Probably when I go to the module 4 and 5, I will show my idea how to design a counter, how to use combinational concept in the design of counters. Understand? Whenever you want to increment from one state to the next state, use combinational part. Whenever you want to store the states, use sequential part. When I say store, you need a flip flop. When I say increment, you need one adder. Okay. So these concepts I am going to use in the counter design. I am going to show you Verilog code for that. If we can adapt that kind of the coding standard in all your designs, whether it's in different applications, you can do a better counter design for it. Alright. I just want to go through this. All flip flops change simultaneously after the appropriate propagation delay associated with a single flip flop. You must know, last class I discussed about propagation delay in ripple counter. What is the propagation delay of a ripple counter? The formula I told you. Remember that? N into TPD. Total propagation delay is nothing but N into TPD. What is N? Number of stages. TPD is nothing but T subscript PD, propagation delay. Propagation delay of each flip flop. Understand here? Suppose if there is a 4th stage, if propagation delay of each flip flop is 10 nanosecond, how much overall the delay in the 4th stage counter? 40 nanoseconds, right? That's a propagation delay of asynchronous counter. We should overcome that propagation delay in the synchronous counter. How do you define propagation delay? Pardon me? Yes. How much time a gate or circuit can take to produce the output when the inputs are applied? Understand? But how do you define this for the sequential circuit? The definition holds good for combination circuit. Because there is a combination, let us say for example AND gate, you give input, output will be ready, that's the propagation delay. You can't experience the delay, but there is some delay associated with each and every gate. I am asking, how do you define propagation delay for the sequential circuit? Yeah, that's very important. Understand? Whenever I say sequential circuit, two things you should not forget. I keep telling always the train, which is equal to what? Which is analogous to clock, and passenger is analogous to data input. Understand it? These are very important when you focus on the sequential circuit. Now tell me, how do you measure propagation delay in this? Clock must be there, data must be there. Train must come, passenger must be ready. Understand? Having these two, how much time the flip flop will take to produce the results? Clock must be there, rising edge must be there. When rising edge comes, when the inputs are applied, how much time flip flop will take to produce the output? You can't alone decide by the input for the sequential circuit. Understand it? There is a different definition for propagation delay when you look at sequential circuit, because sequential circuits are associated with memory. It also depends on the clock. Clock and input both are important in case of sequential circuit. Alright? So, propagation delay associated with single flip flop, because here in synchronous counter we apply clock for every flip flop. That's important. Count pulses are applied directly to the control inputs. Control input you can call as a clock. Many times we use control input as a clock only. Look at the label notation. We use here C. C stands for clock flip-flops. There are various experts in industry who design the clock itself. The experts are called as clock tree synthesis. Their no objective or aim is to identify which block, how much frequency clock is required. Understand what do you mean by clock tree? There is a source clock. There are hundreds of the digital blocks exist. I'm giving example, real practical design. Hundreds of digital blocks exist. Assume that 1 gigahertz source clock exists. Some block required just 10 megahertz. How do you design clock for the 10 megahertz? Though source clock is 1 gigahertz. Let's take practical laptop itself. What is the typical frequency coming with the laptop? Typically 3.33 gigahertz. That's the frequency which clock can generate within the laptop. Now see, source clock is how much? 3.33 gigahertz. Let me assume that within this laptop there are 100 blocks. You can't expect all blocks to run at same frequency. Understand here? You can't expect all blocks to run at same frequency. Though classes second hour starts at 9:30, you can't expect entire college to start every class at 9:30. Some classes will start little later, it will end up little later. Understand? That's how digital blocks also work. Understand here? Each block requires different frequency. That's called clock tree synthesis. You must use source clock and divide that clock into the requirement of individual blocks. A one block may run at a 0.5 gigahertz, another block may run at 10 megahertz, or there are blocks which can run at few kilohertz also. Understand it? The objective of clock tree synthesis is you must identify what is the clock requirement for each and every block. Understand it? And design proper circuitry for that so that clock distribution is done without affecting the entire performance, overall system performance. Understand it? That's very critical. Let me tell you all these kind of things. Okay, that's why I insist you to involve in small designs first. Understand it? Involve with just the 3 blocks, 4 sub blocks, how to design clock for that. Then go for very big design. I'll tell you without effortlessly you can design the clock for the 100 block, 1000 blocks. Understand? You must have that confidence. If you do small designs, you will gain that confidence. Okay. All flip-flops change simultaneously after the appropriate propagation delay associated with the signal flip-flop. Every flip-flop will have its own propagation delay. Okay. After that, you will see the results at the output. This already we have discussed. Just go through the important points within this. This is the example for synchronous binary counter. Look at how the circuit is connected, construction is made. Understand it? There are 4 flip-flops here. This is a 4-bit counter. And counter outputs are labeled as Q0, Q1, Q2, Q3. Understand it? This is sequential circuits. We don't have any input here. Only input for this is the count pulse and the count enable. Count enable is just like a main switch. Understand it? This main switch. Once you turn on this, what will happen? And this is also required, right? This is like a heartbeat, the count pulse. Understand it? When I say heartbeat, there is a rise, spike and downs, right? Clock is like a square wave. This will keep on coming in the square wave, will keep on coming here. But look at here, this every flip-flop what you are seeing here, they are active for the rising edge because you can see the symbol here given. Whenever the rising edge comes here, all flip-flop will be triggered simultaneously. And they will change the states. What do you mean to changing the states? Presently, where they are, you must also see that because they store data. There are the feedback elements, right? In the very beginning, we told how to construct a flip-flop. We started from a latch, if you look at not gate based latch. Then we moved to the NOR gate, then the NAND gate, and we added the gated flip-flop, gated with the clock. So much of discussion has happened in that direction. Now we are working on symbolic representation of the T flip-flop here. Okay, whenever here 0 comes here, this remains in the same state, no change in the state. Whenever 1 comes here, there is a change in the state. Flip-flop will go into the toggle mode. That's the working principle of T flip-flop. Now here clock is applied common clock for all the flip-flops. And look at here. Now T input now, for the first one we give it from the count enable. That remains 1 always whenever you want to make this counter to count in upward direction. And then we can see that the same count enable goes to the input of every gate. AND gate is now, it doesn't make it as a 1 year until the both inputs are high. The working out AND gate works. Now one of the input is coming from the count pulse, other input comes from the previous flip-flop. Okay. Now this gate will become 1 only when this Q0 is 1. Anyway, this count enable you are making permanently 1. Understand? So count enable is 1 for all the AND gates. But look at here now. Once the first clock pulse is applied here, only this will change the state. Once this changes the state, it becomes 1, and now this has 1. Already this is other input of AND gate is 1. Then the AND gate output will change the state. Though AND gate output is combination circuit, it is changing state. This state will not propagate here until the second clock pulse comes. Understand you? From here to here, look at this. I am putting my hand here. From here to here, data will propagate only on the occurrence of the clock. First clock, this data here, let us assume 1. This change in the state, this change of state, this has propagated here. This is immediate because it's a combination circuit. No, this will not wait for anything. It only requires input, and if input is given, then output will produce without any, the hazard here. Now output is produced here, and from here to here, it all depends on the clock. Understanding? Already first clock pulse has been passed. When the first clock pulse has been applied, this changed the state, but this will not change its state. Reason is, gate input was 0. No, previously what was the Q0? It was 0, right? When 0 was coming here, what was the output of an AND gate? It was 0 only. Understand it? So when the T is 0, what will happen to the output of a T flip-flop? It remains in the no change state. So Q1 will not change the state. Even the first clock pulse when it is applied. Only when the first flip-flop will change its state from 0 to 1 in the first clock pulse. When second clock pulse is applied, though data is available here, for the first clock pulse, this will not change. Okay. After second clock pulse, this will change state. These two will not change states. And after third clock pulse, all three will change states now. Okay. And look at here the fourth clock pulse now. This will change state now. Because the AND gate output is coming from the previous flip-flops. Understand? Suppose if I call this the ith flip-flop, this will be I minus 1th flip-flop, I minus 2, I minus 3 like that. Okay, that's how the flip-flop works. Okay, look at here, the AND gate preceding each input T detects if all lower order flip-flops are in the 1 state. AND gate output will be 1 only if all the lower order flip-flops. Lower order means if you are looking at this particular AND gate, you should look at lower order flip-flop is this. If you are looking this AND gate, lower order flip-flops are these two. If you are looking for this particular AND gate, these are the 3 flip-flops are lower order flip-flops. Until they becoming 1, this will not change, the output of AND gate will not change. That's how it is been written here. So lower order bits are in 1 state. If yes, toggle some positive clock edge. Drawback of the circuit is there are so many inputs going to the AND gate. Understand? Look at this one. Second one, 2 inputs. Third one, 3 inputs. Fourth flip-flop, 4 inputs. Assume that you are designing 1024 stage counter, synchronous counter. You must design an AND gate with the input as 1024, which is quite difficult, right? So what is the drawback of this one now? As number of stages keeps increasing, number of inputs going to the AND gate also increases. Is it good, increasing the inputs to the AND gate? Have you come across fan-in, fan-out in the logic design? Fan-in is number of inputs a gate can have. Fan-out is any number of gates a gate can drive. Understand it? How many gates it can drive? Understand it? For example, if I am a person, I can handle just the 10 kg weight. If you give me 100 kg, what I will do? I will try out. Understand it? Same way, every logic gate will have its input limitation and output limitation. Understand it? You can't connect so many gates. This AND gate cannot drive so many logic circuits. This situation will come across in the system design. Look at in the laptop. Don't you think that every gate needs many more ICs? Yes or no? Your processor needs to drive hundreds of ICs. How are you going to overcome that fan-out problem in the case of laptops? Using buffers. Use buffers. Have you come across buffers? Buffers will amplify, they will boost the levels. That's why you see in computer design, okay, in processor design, every output we connect what is called as a buffer. Understand? You may think that it is a waste of hardware, other things, but buffers will boost your current levels, voltage levels. Understand? Suppose if you are connecting, say, monitor kind of monitor requires one particular IC. Okay, the data coming from the processor has to go to the monitor. That needs an IC. Your processor will not send blindly the data to the monitor. It sends to the corresponding IC, peripheral IC, and then it display the data on the monitor. Like that, if the CPU has to drive many more ICs. Okay? Any questions about this? I hope you understand the problem of this, because circuit will become complex if you go for more number of stages. Okay? How do we work on that? This is a small change in the AND gate drive now. Instead of giving lower order flip-flop inputs to the AND gate itself, look at here what we have done here. This is a flip-flop, output comes to this, and count enable is that. Look at earlier we gave count enable to all the AND gates, but now we did not give count enable to all the AND gates. Count enable goes to this, and output of this goes to this. Understand? Is it like a ring now? It looks like a ring, right? Look at here. This. Just a cascade kind of arrangement. Okay? This output goes to this output goes to this. Understand it? This is another way. The drawback of the circuit itself is it is the next gate depends on the previous. It just like looks like a ripple only. Got it? The working of this remains same as this, no change. And counting states, though we have not mentioned. In the very beginning, I showed you what is the counting sequence. Look at this counting sequence. I'll just show you this is the counting sequence. Binary counting sequence. For all the 4-bit binary counter, what I have discussed, this table remains same. This is the counting sequence. Starts from 0, 0, 0, all 4 zeros. Q0 to Q3 are the outputs. And once all states becomes 1, it resets back to the 0. It keeps repeating like this. Understand? For all the counters, whatever I discussed. Again and again, I did not write this table. It's understood that whenever I discuss either synchronous counter, asynchronous counter, this table holds good. Okay? Let me move to the next one. We discussed this. There is no change in the design. It proceeds same. But the question is now here, inputs have been reduced comparatively with the first one. If you look at the first circuit here, the inputs has been reduced. Now, even if you go for 100 stages, the AND gate needs only 2 inputs, not more than that. Okay. The output of AND gate preceding the ith flip-flop consists of the inputs of the AND gate preceding the I-1 flip-flop. That's 1 flip-flop input is sufficient here. And the output is Qi-1. So both output is required and the count enable both are required, and that can change the state of the T value here, and that again triggers whether toggling mode or same no change mode, that is decided by the T input here. The working principle of this remains same as this, no change in the counter. Let me move on to the mod M counter. Mod M means M stands for number of states, and generally flip-flop will have 2 to the power of n states. Many times we may use or may not use all the states. I showed you the 4-bit count, right? How many states it has got? 16 states. Sometimes some applications may use all states, or some applications may use partially the few states. Okay, it all depends on the applications here. Now I'm going to discuss one particular circuit, which is very complex circuit, and this is a commercial counter available in the form of an IC. I'm going to explain that IC, the internal circuit first, and later we will show a block diagram representation of that IC. Okay, and for that we call that as a mod M counter, and counter uses JK flip flops instead of T flip flops are used here in the counter, and counter will have enable. Enable is required to load the data parallelly. If you want to load any predefined state, that can be done through D0, D1, D2, D3. They are the inputs, and the count enable allows for counting. Whenever you make count enable as 1, counter will start counting. The question is now, load enable will be given high priority. Okay, once you know if you make load enable as 1, it expects data from D0, D1, D2, D3. Okay, this is how the preamble of that counter design. Look at this is the circuit. So for whatever I given preamble for that, this is the circuit. Look at here now. Nobody will ask you to design this in the examination. You may have to just understand, as I told you this is going to be the IC available like this. But internally, if you look at circuit diagram is like this. Okay? And this IC will enable you to do higher order counters also. But this single IC, it will have only 16 states, Q0 to Q3. There are 4 outputs, 16 states it can produce. And look at here, there is a load enable, there is a count enable. Same thing you are seeing even in IC also. Okay, there is a load here, count here. D0 to D3, there are the 4 inputs. And C is nothing but clock, rising edge. And look at outputs here, Q0 to Q3 are the outputs. What is CO? CO is nothing but carry output. And this is the one, we can use it for cascading the counters. When all these 4 outputs are 1, at that time the CO becomes 1. Okay? Whenever CO is 1, what I can do now? I can use this as a count enable for the next one. I can use similar IC one more and cascade this and build higher order counter based on this signal. Understood? When CO is going to become 1, what is CO? CO stands for carry out. Whenever all these gates are 1, Q0 is 1, Q1 is 1, Q2, Q3 all are 1, at that time the CO becomes 1. Otherwise, CO remains in 0. Understand? Don't make noise. Any questions about this? Okay, you can also check here how this works here. This is an internal circuit diagram. Suppose if you make load enable as 1, what will happen now? What is load meaning? You have to apply the input data. Load enable expects always D0, D1, D2, D3. You give binary data here, either 0 or 1, and that will get loaded to the flip-flop inputs. For simplicity here, this IC uses JK flip-flops, not the T flip-flops. Okay? All are JK flip-flops, which has got 2 inputs here. You can see it, 2 inputs. One advantage is using T flip-flop, it will reduce the number of inputs also. But here they are using the JK flip-flop. Look at here, there is a carry out here, which I already showed you here. There is a carry out. At the count pulse here, there is a clock pulse which we are going to connect here. Whenever the clock comes here, depending upon the J and K, this may or may not change state. If it is 0, 0, you already know the working of a JK flip-flop, right? For 0, 0, it remains in no change state. For 0, 1, it becomes 0, 1 only. This is Q0 at 0. For 1, 0, this becomes 1. For 1, 1, this goes to the toggle mode. Understood? So based on that, we can understand the working principle of everything, the construction also. And look at your count enable. What happens when both are 1? What happens when both are 1? As I already told you that when both are 1, this is going to take priority. Understand here? It will ignore the count enable and load enable will take the priority. That means this expects our D0 to D3 data should be loaded here. Okay. Next, if you make load enable as 0 and count enable as 1, and if you apply here clock pulses and count pulses, this will work like an up counter. When I say up counter, states will be 0, 0, 0, it count all the way up to 1, 1, 1. When all are 1s here, this carry output will be 1. Okay? This is a binary. You can use this as binary up counter. Understand? This we can also use this as no change state. Just look at for various combinations of count enable, load enable, how this circuit works. Okay. The explanation has been given here. This using this, you can just explain the working of counter. And this is again, look at this example. This counter, you have made changes in the IC such that it counts from all 4 zeros to 1001. After reaching a state 1001, it resets back to 0. That is done by using an AND gate here. And look at here, Q0 when it is 1 and Q3 when it is 1. These two outputs are connected to the AND gate. When both are 1, Q0 and Q3, then the AND gate output becomes 1. That is loaded with zeros. Okay, so counter will be resetted with zeros when the AND gate input is 1. Therefore, counter will become reset now. Okay, That's how this counter can be. This is called mod 10 counter. Just by changing connections, you can construct mod 10 counter. You can also construct mod 8 counter. Understand? But maximum states is all ones. In that, any counter can be designed. Any mod counter can be designed using this IC. This is commercially available IC. Look at here. There is an example of showing how to use carry out to design high-end counter, 8-bit counter design. Understand? Previously, I showed you 4-bit counter. With single IC, you can design 4-bit counter, which counts from 000, 0th state to 15th state. Okay? This is 8-bit counter. In order to construct 8-bit counter, you can use in a cascade fashion. Look at here. The CO carry out is used as input for this. Okay? This is an 8-bit counter. It is building an 8-bit counter using two 4-bit counters. This is just an example sake. And now counter based on the shift register. This all I think you might have done in the laboratory. I don't want to elaborate this. These are the counters which are based on shift register. You can see here, output of this is connected back to the D input here. And as count pulses keep on applied here, this will start like the states are shown here. You can see here. Q, A, B, C, D. If you give here one input here, it starts from 1, 0, 0, that is the first state, 0, 1, 0, 0, second state, 0, 0, 1, 0, third state. Totally you have 4 states here. That means here we are using counters using shift registers here. This is called ring counter. Okay. This is another counter based on shift registers here. You can see here we have connected here Q0 bar back to the D input here. Okay, this is called twisted ring counter. Okay, you can see that how it works here. See, this Q0 is connected back to the D input here. Whenever Q0 bar is 1, at that time, this will change the state. Okay, the first flip-flop will change its state. This is called twisted ring counter. Just go through the states here. First state will be the, the first state will be all zeros. And you can see here the QA has changed to 1 because this complement of this goes to the first input. QA has changed to 1. And again you can see here now the second state is 0, 1, 0, 0, 0. Please don't make noise. The third state is 1, 1, 0, 0. The same one will be propagated to the first state here. And you can look at here, when all becomes 1 here, and again see the complement of this becomes 0, and therefore it starts again from 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, and again back to the all zeros. That's how the twisted ring counter works. This is again another version of twisted ring counter. We are connecting here third flip-flop, fourth flip-flop output, complementary output to the AND gate, and AND gate output is given to the D input here. That's about counters. Any questions? Not very nice. Any questions you have? So this topic seems to be very easy. Until unless you don't practice it, you can't get it. I've seen most students, I think that right now can do well, but ultimately how many you can write the examination that matters. Many times easy things will confuse you many times. And so practice is all these things whatever we discussed. Okay. I will show you now how to design one counter step-by-step procedure, and you can apply this concept for counter design with other flip-flops. I will show you first the JK flip-flop. Okay. I will show you the mod 6 counter. You can apply similar concept to design for other counters also. Mainly this kind of questions will be asked in gate examination. I'll show you one. For this, what you need to remember is the excitation table. You remember the previous class we discussed about excitation table? Yes or no? We discussed when the present state is known, when you want to know the next state. If I know the present state and the next state, what is the input required? That's not excitation. You should practice that. You should add all those excitation tables so that you can understand the counter design. Look at this. These are states which I am expecting from the counter. And these are not binary counter. Are you seeing any binary counting here? Is a binary counter? It's not a binary counter. What kind of code it is? Anybody can guess? What kind of pattern it is generating? XS3. XS3 means you should see 0, 3, 6 like that. For 1 it will be 4, for 2 it will be the 5, that is XS3. It will be XS3. That code is different. Now come across gray code. Gray code. The person who invented gray code himself is gray. His name itself related to gray. Very popular course in communication system. Why I am saying it's popular in communication system, electronics communication. In error we encounter while transmitting bits. You remember error correcting codes. Today's information is transmitted through binary only, nothing else. While transmitting from the transmitter to the receiver side, how do you ensure that receiver has received proper data or not? Supply some error correction there, error checking mechanisms over there. In that correction, this gray code will help you there. And also make an observation here, from one state to the next state, there is only one bit change, which KMAP also follows this. I've seen that. Let's not worry about the pattern what it is generating. I want you to observe here, one state to the next state, there is only one bit change. Are you seeing that here? Let us assume that 0, 0, 0, all three zeros, that is one state. Look at the next state. So 0 has been changed. See, I am not interested in what pattern it is producing. I am interested in, from here to here, there is a one bit change. No change, there is a change here. Understand here? And look at here, from here to here, no change, there is a change here. Even in KMAP also you have seen, right, while writing the binary pattern in the column wise and row wise, we used to follow the same pattern, right, in the KMAP also. Okay, it's a powerful way gray code helps in error correcting mechanisms. Look at this two, no change, change. Okay? Two changes here? No. Look at here, 1, 1, 1, 0, 0, 1, there is a 2 change. Here 1, 0, and this pattern has been given here. What we expect from this one is, we expect the count, we need to design a counter with the JK flip-flop, and this pattern is given here. Using this pattern and using the excitation table of a JK flip-flop, you must design the counter. This is the 3-bit pattern, because if you see previous table what was shown, just look at here. There is a 3-state. This is a 3-bit here. We need 3 flip-flops. General network looks like this. Okay, this is a logic network which we must design here. Okay, look at what is the data inputs coming to the logic network. This is the first flip-flop, FF1, FF2, second one, third flip-flop, and we have preferred JK flip-flop. Look at our title. We are showing you how to design synchronous mod 6 counter. Mod 6 means there are 6 states. All 6 states are shown you already. It has some pattern in that. They are not binary counters. They are non-binary counter. Some pattern they have given to you, and that pattern you must design using this network. And based on the pattern, there are 3 outputs. 3 flip-flops are required. You have taken JK flip-flops, and JK flip-flop will have normal output, complementary output. And here this is a logic network which we are designing, and we'll show that once the design is completed, what must be the circuit here, we'll show that later on. But for this logic network, Q1 is the input, J and K goes from the logic network. Look at here, J1, K1, first flip-flop inputs goes from this logic network. Similarly, J2, K2, J3, K3. And outputs from this normal output, complementary output comes from the flip-flop itself. That means this block will receive, gives the input to the flip-flops, and also it receives output from the flip-flops. Okay, that's the general block diagram. Now let me show you how the table looks like here. This is what I am calling as excitation table. If you remember we have shown how JK flip-flops works. Okay, from the present state to the next state. This state is already defined. I did not expand with this. I already have shown in the very beginning what pattern the designer is expecting. He expects pattern something like this 0, 0, 0, 0, 1, 0, 0, 1, 1, like this. And look at here, if you have this pattern already defined given by the designer, generating this is very easier. If it is 0, 0, 0 as a present state, what is the next state you expect? Next state is 0, 1, 0, that comes here, right? Understand here? Present state is all zeros. Next state, what you expect here? This is called next state. Q1 plus, Q2 plus, Q3 plus. Normal outputs. And we expect a state as 0, 1, 0. And if 0, 1, 0 is the present state, what will be the next state? It is 0, 1, 1. How do I write this one? Based on previous table what I showed. Just look at this. You yourself can generate this table. First two columns. Now, can you write this? What I am writing here is, if this is going to be the present state, next state is this one. Understood? If this is going to be the present state, next state is this. Understand? We written there are two columns there. If this is going to be the present state, what is the next state? This is the next state. It goes back to here. Understand it? Based on this table, pattern given, we have designed here the excitation table. I hope you are clear with first two columns. Any questions about first two columns? Okay? Okay, now find how to write this one now. Now here it's very important, you must know we discussed in characteristic equation, how to write. If you know the present state, we already know what kind of flip-flop I'm using here. I'm using JK flip-flop. And JK flip-flop, first flip-flop will have J1, K1, J2, K2, second flip-flop input, third flip-flop input is J3, K3. And for let us see first flip-flop inputs, I will generate this. First flip-flop in output is this. 0 is the present state, 0 is the next state. What is the J and K required? How do you get that? Forget about these remaining columns. I'm just looking at these two only. J1 and K1. I'm observing just J1 and K1. I am asking you a question here from previous function table what we have discussed. This is the first flip-flop output is 0. I know next state is 0. From 0 to 0, what is J1 and K1 required? You want to see the table here? For your reference, I will this is for D flip-flop. I will see if JK flip-flop table exists. I will show you. I don't think. Yes, look at this one. Are seeing this? This table has been used in that. Present state is 0. Next state is 0. What is J and K required? 0, 0 is here. Where else we have 0, 0? 0, 0 is here, right? Look at these two. Present state is 0, next state is 0. Present state 0, next state 0. What is J and K required? J required is 0, K required is don't care, right? Are you getting this? Yes or no? I'll explain you once again. Look at this is the present state, this is the next state. In our table, you look at here, what I want here is, what I need here is, look at here. I'll just move to the, yeah, look at here now. Present state is 0, next state is 0. What is the J and K required? Here I have written as 0 and don't care. Hyphen means here don't care. Now let us go back to the table what I showed you, look at here now. Present state is 0, next state is 0. Like this I have two rows, right? Look at here also. Present state 0, next state 0. These two rows you observe it. And look at what is the J and K required for that. J required is 0, 0 to 0, there is no change here. But look at here, K required for 0, 0, change. K required is don't care, right? Same thing I have written over there. Okay? I hope you understood this. Look at now here. So, J required is 0 and K required is going to be, K1 required is going to be the don't care. Now, next, let me move to the next one. I'm just looking at only J1, K1 design right now. I am not interested in other flip-flops for the time being. Present state is 0, next state is 0, same, 0 and don't care. Look at here, present state is 0, next state is 1. What is J and K required? Don't look at this answer. You write that from the previous table what I showed. Present state is 0, next state is 1. Let me go to the table once again. 0 and 1. Look at now. Where is 0, 1 here? Now here we have 0, 1 here, 0, 1 over here. Look at these two rows. Present state is 0, next state is 1. Present state is 0, next state is 1. What is J and K required for these two? Look at here, K is again don't care, but J is what? 1. So 1 and don't care is going to be the inputs required. So let me show you that. Look at here now, 1 and don't care. I hope you got this idea, how to write this one. Okay. Similarly, can you look at for J2, K2? If you want to see J2, K2, look at here Q1, Q2. Q1 and Q1 plus, not Q1, Q2. Q1 and Q1 plus. Present state is 0, next state is 1. What is J2, K2 required? It's 1 and don't care. Present state is 1, next state is also 1. Don't care and 0. You want to see the table, excitation table. Previously what I showed you, the function table, you should see that and write all these things. Once you fill out this, you are supposed to use the K map and arrive at a Boolean equation. Look at this is a K map. For every row, what I showed here, this one, J1, you have to write separate K map, K1, J2, K2, J3, K3. Totally you are supposed to use 6 K maps. All 6 K maps are shown here. Look at here. This is J1 equation is Q2, Q1. K1 equation is Q2 bar. You have to make an entry of the previous excitation table shown here. 0, 0, 0, 1. That was the excitation table. If you want to know that, you can just look back the previous one here. Look at here. 0, 0, 1, and this is going to be the 0. You can give a number here, and then you can write this. This is 0th line. This is 2, and this is 3. 0, 1, 1 is 3, and 0, 0, 1. 1 is 0. Okay? That means you write for this particular pattern, what is the J1, K1? You just make an entry in the K map, and you can see here, and there's a pairing made here. Based on that, we got this as a Boolean equation. Once you know J1, K1, similarly, you can also obtain J2, K2, J3, K3, and you can arrive at logic circuit like this. And previously, what I showed the logic network, nowadays it contains a network like this. This is how one can design the mod 6 counter using JK flip-flop. Any questions about this? If you understood, or is there any question, is there any doubt regarding this mod 6 counter? Any pattern can be given in examination. Just I showed you one particular pattern here, a non-binary pattern. This is a pattern which is given to you. I may change data and ask you to design a, see here I have discussed mod 6. In examination I may give you mod 5. I may give you mod 8. And ask you to design counter using, I showed you in JK flip-flop. I may ask you to design mod 5 or mod 7 counter using D flip-flop. The concept remains same. Because in fact, D flip-flop and D flip-flops are very easy to design a counter. Reason is number of K maps you see now. JK, how many required? Probably 6 for 3-bit counter. 6 K maps you are supposed to reduce it. It becomes complex. It's a tedious job here. Okay. So practice this, and as shown here in this for the JK flip flop. Similarly, one can do even for D flip flop also. This is the application table for the D flip flop. Given the present state, next state, D input required is 0. Present state is 0, next state is 1, D input required is 1. Based on this, you can write the excitation table. Look at here. Present state is 0, next state is 0, D1 required is 0. You see the previous table and you can arrive at this. These two you can easily construct. Once you have done that, you can use K-map and arrive at Boolean equations, then write the logical network for that. Similar thing you can go for T flip flop. Look at here, this is the application table for T flip flop. This is the excitation table for T flip flop. Boolean equation for T flip flop. Here logic network is not shown. We are shown only for the JK flip flop. For this, based on Boolean equation here, you can construct the logic network. Understand? Any questions? This completes, the counter design, and I hope you have got a lot of more details related to the counter. Practice all this design. Okay. When we discussed counters based on shift register, I also showed you commercial form of counters available with all necessary inputs. How you can build, the high-end counters like 8-bit counter. Understand? Count is very easier topic to score you well in examinations. In the remaining two modules, we'll focus on the Verilog HDL. That's very important. So far, whatever we discussed is theoretical aspects. For practical aspects, we have to move to the module 4 and 5. There I will show you, I will have a software here. I will show you each and every design, how it can be simulated. Probably if you have a laptop, you can use that same software, Model Sim, and you can simulate it. Yeah. No, I am using Model Sim. This software I am using, Model Sim. This is a classic software which our college doesn't have it. And I am using a cracked version. You can also use as long as you are not using for commercial purpose. For academic purpose, you can use this software. It's a very good tool for simulating all Verilog, VHDL, System C, and a lot of other hardware description languages. See, look at here how very easily you can simulate. You can write Verilog code by going to the work library. It produces a lot of waveforms. I will show you that in the next class. It takes a lot of time for you to understand this waveform pattern. Okay. I will show you simulation and other things in the next class. Okay. I will take attendance meanwhile.